A really important technique in integration is called the substitution rule. It's also called U sub. If I take the integral of cosine x dx, that equals sine x plus c. We might think that if I take the integral of cosine of 3x dx, that equals sine of 3x plus c, but it doesn't. And we can see that by taking the derivative of the right-hand side. If I take the derivative of sine 3x plus c, I get 3 cosine 3x plus 0, or 3 cosine 3x. That's by the chain rule. So that doesn't work. But after knowing what I just did, what if I said that the integral of cosine 3x dx was equal to 1/3 sine 3x plus c? Now let's take its derivative. If I take the derivative of 1/3 sine 3x plus c, I get 1/3 times 3 cosine 3x plus 0. Again, that 3 comes from the chain rule, which is equal to cosine 3x. So I was able to, with trial and error, able to figure out how to do this integral. But I'm not a big fan of trial and error. I'd like to come up with a systematic way of doing this. So let's come up with a systematic way of doing this. I'm going to go through a proof. I don't need you to be able to recreate this, but I want you to understand where this comes from. I'm going to talk about a composite function, capital F of g of x. I'm going to say that capital F of x is the antiderivative of lowercase f. That is, lowercase f of x equals the first derivative of capital F of x. If I take the derivative of f of g of x, I get this by the chain rule. I can rewrite this first part of the product as this. So I can think of capital F of g of x as the antiderivative of lowercase f of g of x times the derivative of g of x. If that's the antiderivative, then when I take its integral, I'll get back to the antiderivative. So I can write this equation. And here's where I get into the word substitution. I'm going to substitute f of g of x with f of u, and I'm going to substitute g prime of x dx with du. Then I can write the right-hand side of this equation as capital F of u plus c. I can summarize the substitution rule as such. I'm going to let g of x be u, and g is going to be integrable on a specific interval. And f will be continuous on that range of g of x on that interval. In that case, the integral of f of g of x times g prime x dx equals the integral of fu du. Let's write this out in terms of steps. The first thing we need to do is identify that inner function g of x. And we need to pick that g of x such that a constant multiple of its derivative is in the integrand. We substitute u equals g of x and du equals g prime of x dx into the integral. We evaluate the new integral, and the last step is to rewrite things back in terms of x. Don't leave it in terms of u. This doesn't always work. Not all integrals will be able to be solved using substitution. Let's look at a few examples. Let's start off with some super nice examples. For instance, the integral of 3 times 3x plus 1 all squared dx. The reason why this is super nice is my inner function and my derivative are already there for me. That is, if I let my u equal 3x plus 1, my du is 3x dx. There's nothing I need to do to this. So I end up with the integral of u squared du. And when I go ahead and solve that integral, I get 1/3 u cubed plus c. And then remembering I can't leave this in terms of u, I rewrite this in terms of x. And that's my final answer. Here's another really nice example. My inner function is going to be my 11x, and when I take the derivative of u with respect to x, I get 11 dx, which again is right there and nothing else. I simply rewrite this as e to the u du, and the integral of e to the u du is simply eu plus c. Again, I cannot forget to put this back in terms of x, and that's my final answer. They're not all this nice, however. Let's look at this example. My first guess would be that my inside function should be this. That is, u should be equal to x to the 4th plus 6. When I take du, I get this is equal to 4 times x cubed dx. The trouble is, I see an x cubed dx in there, but I don't see a 4. So what I'm going to do is solve for what I know I have. I have this x cubed times dx, so I'm going to solve for that. That is, if I divide both sides by 4, I end up with du over 4 equals x cubed dx. If I replace my x cubed dx with du over 4, then this is what my integral now works out to be. And when I do the integration, this is what I end up with. Again, the final step is always to rewrite this back in terms of x. U was equal to x to the fourth plus 6, so I'll just go ahead and substitute that in. And there is my final answer. Again, I could check these by doing derivatives to make sure I get back to what I started with. And if I go ahead and do that, I find that I end up with, in fact, my original integrand. Let's do one with trigonometry. This type of problem you're going to see a lot. If you see a cosine and a sine, and I see something like cosine to the third, I'm pretty sure I'm going to let that be my u. And since I know the derivative of cosine is negative sine, I'm pretty sure I have that sine in there. I'm just going to have to take care of that constant of a -1. I'll let u equal cosine x. I'll let du equal negative sine x dx. Since I have sine x dx, I'm going to solve for that. And then I'm going to replace that with negative du. Here's my integral. I'll go ahead and integrate. And finally rewrite this back in terms of x. Here's a really not nice example. To be honest, once you get to Calc 2, you're going to find out better ways of solving this, but you'll have a few of these on homework. If I have this integral, I might guess that first I'm going to start off with u being x plus 1. In that case, du is simply equal to dx. The trouble is when I do my substitution, I'm still left with an x. Once I'm in u world, I need everything in terms of u. I don't want any extra x's in there. But I can actually do a trick, and this is a kind of hokey trick, and you'll have to do it once or twice on homework. I can take my u substitution and solve it for x. When I do that, I can now replace that x with a u minus 1. To solve this, now I'm going to have to split this up into two separate integrals, simplify my first term, and continue with the integration. Again, once I am done with this, I need to substitute back into the x world. I could do some factoring to simplify this a little bit more, but quite honestly, I'm quite fine with this on an exam, and your homework will accept this as an answer. Some books will give you tables of standard u substitutions that are easy to memorize, but to be honest, since you might not always get them in that form, I'd rather you just use a u sub instead of doing memorization. There are tables available if you'd like to memorize those instead of working through this, but I'm not going to go through using the tables. There's one more thing we have to worry about, and that's definite integrals. I also call this, what about those pesky limits of integration? Because once I leave the x world and go into the u world, those limits of integration are going to be different. That is, I have to plug those values for a and b into my function that is u, that is my g of x. That is my g of x. So let's use an example because I think it's easier to see this with an example. For this, it's pretty easy to see what my u should be. My u should be x plus 3. My du is simply dx. From there, I can rewrite my integration like this. But I have to take care of my limits. So I can do one of two things. I could either write that this is g of 0 and g of 2, and then kind of ignore those until the very end. That is, I'm going to go ahead and integrate this, and I get that this is equal to -1/2 u to the -2 evaluated at g of 2 and g of 0. I haven't figured those out. In fact, I'm doing that on purpose in this first method because what I'm going to do is first bring us back to x. When I do that, I replace the u with x plus 3. And now, instead of worrying about g of 0 and g of 2, I can go back to my x numbers and call it 0 and 2. And when I do that, I get down to the fraction 8 over 225. I could have done this a different way. I could have gone ahead and found what those g of 0 and g of 2 values were and never go back to x. If I find that g of 0 is 3 and g of 2 is 5, I can, instead of leaving it in terms of g2 and g0, I can plug those numbers 3 and 5 right into my u. So in this case, I don't go back to x. The method you choose is entirely up to you. I prefer the first method. I don't like making mistakes with calculating what g0 and g2 are. I'd prefer to leave those alone, bring it back to x, and then just plug in those values directly. However, with the second case, it's a little bit less work because you don't have to actually go back in terms of x. So either one of these methods work, but just don't mix them up. Here's one final example, and I'll do this both ways. Again, in this case, I'm going to have u equaling sine x. and my du equaling cosine x dx. When I rewrite this, here are the two different methods. The one on the left, I go ahead and find what g of 0 and g of pi over 2 are, and then I plug those directly into my u and I get 1/5. On the right hand side, I rewrite my u as my sine x, and I have sine to the 5th x, and then I plug in the 0 and pi over 2. Again, either method works.